Hi, my name is Tianyu Ma. I would like to present my work for ISBI 2020, Volumetric landmark detection with a multi-scale shift equivariant neural network. This work is done by me and my collaborator at Cornell University and Weill Cornell Medical College. The problem we want to tackle is as follows. Given an image, we would like to identify landmarks or key points correspond to certain salient or anatomical features. It has a lot of computer vision applications, such as identifying visual landmarks including nose and eyes, given an image of a face. In this study, we're motivated by the task of detecting the carotid artery bifurcation from a CT angiography image shown on the right. Carotid artery is the major blood vessel in the neck that supplies blood to the brain, neck, and face. Plaque may build up in the carotid artery wall close to the bifurcation and eventually lead to a stroke. Successful detecting of the carotid artery bifurcation point is essential. Its location can be used as a seed point for centerline extraction, lumen segmentation, and more. Typical CTA image are large 3D volumes with high resolution, and this can be challenging for a lot of automatic detection algorithms. Neural networks have been widely used for automatic landmark detection. Common approach is to use a fully convolutional architecture such as UNet to compute a heat map image at the output that highlights the location of the landmark. Since resources needed to train on images will be proportional to the size of data, training and testing for large-scale volumes can be both memory and time-consuming. Thus, our goal is to develop an algorithm for fast and reliable landmark detection which can handle large volumes. We want our method to be both memory and time efficient and has built-in shift equivariant property. That is, when image shifts for a certain amount, the prediction can adjust its value with the same amount of translation. Like we mentioned before, common approaches use fully convolutional architecture to compute a heat map image at the output that highlights the location of the landmark. To achieve this during training, an arbitrary-sized Gaussian blob is placed at the landmark. The volume with maximum value will be the outputting point. However, the output shape is restricted, and the coordinates with maximum value is unstable. Furthermore, the network can be difficult to train due to its sparse segmentation map when the only non-zero part of the ground truth image is a small Gaussian blob. We want to find a better way to convert the heat map to a 3D coordinates. Instead of finding the maximum of the output heat map, we want to use a center of mass layer to find the weighted average of the heat map and compute the loss directly with the ground truth coordinates. In this way, the ground truth segmentation map can take any shape other than being restricted to a Gaussian blob. With the image with a heat map size of 56 by 56 by 56, the coordinates y can be calculated like this, where Vj is the voxel value at the position j. When the input image shifts for a certain amount, the output heat map and thus the predicted coordinates will also shift the same amount. Our method uses a UNet-like network as the backbone, which we call a Localizer net. With our center of mass layer at the end of the network, it is capable of outputting a 3D coordinate given a volume. It consists of a contracting path to capture context and a symmetric expanding path that enable precise localization. For our application, because the input image is very large, it has a dimension of 448 by 448 by 448. It cannot fit into the GPU memory without sacrificing the precision. Our solution is to use a multi-scale approach, making the prediction in a coarse-to-fine manner. All of our input images are 3D, but we only show 2D for illustration purpose. The original 0.5 millimeter high-resolution image is too large to fit into the GPU memory. It has a size of 448 by 448 by 448. So we first downsample it 8 times into a 56 by 56 by 56 image with 4 millimeter resolution. We fit this downsampled image into the first localizer net and have a rough prediction of where the bifurcation point is. Although this prediction is not very accurate because a lot of information is lost during downsampling, it gives us an approximation that can be used to crop the next scale image. For the subsequent stage, the original image is downsampled 4 times and 2 times, and the same size 56 by 56 patch is cropped from those downsampled image around the predicted bifurcation point from previous stage. The image patch is then fed into Localizer net. As the resolution of the input image gets higher, the prediction becomes more accurate. Finally, a patch is cropped from the original image without any downsampling. And the final prediction is made from last Localizer net. I also want to mention that all of our cropping operations are done by resampling the entire image around the predicted points through linear interpolation, so that it is differentiable and our multi-stage network can be trained end-to-end. The loss function can be written as a weighted sum of the mean square error of all stages prediction y1, y2, y3, and y4. The weights in front of each terms represent the relative importance of each stage prediction. We use a schedule weight strategy to train our neural network. In the beginning, alpha 1 is larger compared to alpha 2, 3, and 4, focusing on getting the low resolution prediction correct. When epoch number increases, later stages weight gradually increases, and finally alpha 1, 2, 3 will all be 0, and alpha 4 will be 1. Letting the network really focusing on getting a precise prediction from the high resolution input image. We also want to mention our noise injection layer before cropping the input image for Localizer net. We add random noise up to 5 mm in each direction to the predicted coordinates from previous stage. We then use that shifted coordinates to crop the input image for the next stage. The intuition is like data augmentation to improve the robustness of the model. It can also make the subsequent Localizer net less dependent on previous stage accuracy. This is a figure showing the output heat map from our method in C and D. The regressing Gaussian heat map method is shown in E and F. We can see from the shape of the heat map that it better captures the anatomical structure of the input image, as it highlights the entire vessel, just like this. It is easier to train because it does not restrict the size of the non-zero part of the heat map. Using the center of mass layer also improves the overall accuracy, which we will show in our next slide. We conduct an ablation study of different methods and techniques. Our baseline method is a simple unit with regressing Gaussian heat map method, which gives us an average error of 6.45 mm. By replacing the Gaussian heat map with our center of mass layer, which we call single scale log nag in this table, we observe a decrease in terms of average error to 5.52 mm. As we mentioned before, that our multi-scale Localizer net uses differentiable cropping so that the network can be trained end-to-end. Actually, we can also use non-differentiable cropping, and each Localizer net will be separate. This multi-step approach gives an error of 3.72 mm, which is already better than a patch-based state-of-the-art baseline method we choose to compare against. Finally, with the true end-to-end multi-scale network with our noise injection layer, which we achieve the best performance of 2.81 mm average error, which is about the same as the average Carotid Artery lumen radius. This concludes my talk. I want to thank you for your attention, and I am happy to answer any question during the Q&A session later. Thank you.